is Gerald Zani, and today we're going to show you three effects that can be observed in superfluid helium. The first thing we're going to do is transfer the helium. Now, I will warn you, it's a little bit of a bizarre thing, but we will do the best we can to keep it fairly calm. So, the first thing I will do, this is gaseous helium. This, let me back up a little bit. For those of you who haven't taken 201, there are a dewar, like a coffee thermos. That's what a dewar is. And there's two of these. There's one dewar inside of the other dewar. And Jerry here, 2 hours ago, evacuated the inside dewar, so there's no air in there. And then the outside dewar, this is the inner dewar, this is the outer dewar, he pours liquid nitrogen in there. And the liquid nitrogen cools the glass wall on the inside of the inner dewar over a course of about 2 hours. So a little more details to it, but I don't think it's important bringing that up right now unless you're planning to do this on your own. So this whole system has been cooling for 2 hours at liquid nitrogen temperature. The next thing we're going to do is we're going to bring that evacuated dewar, the center dewar, we're going to bring that up to atmosphere, but if we bring that up to atmosphere with air, it will fill up with water, liquid oxygen, and some liquid nitrogen. And, okay, did I say water? Yes, you said. Okay. So we have to bring it up to gaseous helium. That's why this is here. So I'm going to turn this on. And the fun part is to do this so that you know that you're actually getting helium. You can do that. Don't do it too long, you'll pass out. Okay, so there we go. Oh, hang on. There is the gaseous helium, and let me, okay, go ahead. Okay, now you can hear this little flutter right here, but that little flutter tells us we're over pressure, which we want to be over pressure. So this cap is just sitting here. And so it's an explosion-proof thing. If this outer dewar were to shatter when there was helium in there, the liquid helium would become gaseous helium in about a second. And the volume ratio between a liquid and a gas is on the order of magnitude about 1,000. So if we didn't have pressure relief, and if this system somehow failed, we'd have an explosion. So you always have to have a safety valve. That's, in this case, it's just this little guy here. So we're blowing gaseous helium in there, and now we're going to get all suited up. Make sure we have plenty of nitrogen. Yeah, nitrogen looks pretty good. So this is a tank with liquid helium in it. That's the gas that's boiled off. And what we're going to do is we're going to take this transfer tube, if I can get this to unscrew. There we go. So this transfer tube itself, this is something like $2,000. It's $2,000 because it's very thin wall stainless, and there's two walls, and there's a vacuum between the two walls. So this is in fact a bendable thermos. All right, I'm going to get Jerry this in. Got it? The first thing I'm going to do is I'm going to set this down in here, and I'm going to couple this. So these are O-ring couplings, so I put that down, I screw that down. So we're forming an airtight seal here. Now the reason I'm forming an airtight seal is because this rod is at room temperature, which to liquid helium, which is 4 Kelvin, this is like a red hot poker. So if you imagine sticking a red hot bar of iron in water, all the water will boil off and make pressure. We're going to stick this bar down into the helium, it will boil off the helium, make pressure, and that pressure we will capture to push liquid helium through this tube. So as I go down, this tank is almost empty, so I can hear the bottom. Okay, can you hear that? That means our rod is getting close enough to the helium. It's probably not in the helium, but it's close enough to the helium that the heat from the rod is boiling off helium and pushing helium gas out there. That helium gas is cold and is cooling the inside of this dewar system. So we're going to continue on with that process. Now, ideally, you don't want any fluttering. You hear how that's pretty smooth. If I push this down too fast, you'll get fluttering, kind of an oscillation, and that oscillation burns off unnecessary helium. So if you're really trying to be conservative about your helium, you do this process slowly. See that flutter? So that fluttering is a bad thing, but for instructional purposes. Okay, now I'm sitting on the bottom. And what's going to happen is, first thing you'll see is you'll start to see froth coming out, because I'm guessing that's because the helium is being controlled enough to cause the ambient air to froth. And not too long after that, you'll start to see the liquid. The liquid will actually look a little bit like a blue flame. And once that liquid comes out, then Gary's going to stick that in here. And you don't think, where's my flashlight? Did you say you're
Move the tank back.
Yeah, I will.
Okay, starting to get closer.
Okay, can you see it? You see it's kind of getting a little frosty. And, okay, so we're beginning to liquid very soon. Give them a sec. There, that's the liquid. Okay, go ahead here. Okay, now we're transferring the helium. And I'm going to come over here, and there's a slit in this dewar system. And I'm going to monitor the transfer by sticking a flashlight through this slit. And not accumulating yet. Just starting to accumulate. There we go. Okay. Going like a house fire. Probably done. Ready, Gary? Mm-hmm. 1, 2, 3, up. Okay. Thank you. Put the cap on. Start. That is my right. Why don't you turn on this light, Gary, so I can try to use that. So we're about here. Excellent. Okay, so Jeremy, take it up to the surface, please. Did Ken want to know about this? Yeah. Okay. Focus on the surface there a little bit. So you see how actively boiling that surface is. So the first effect we will see is this means the helium is normal. Once so it's somewhere between 4 Kelvin and 2 Kelvin. Once it goes superfluid, which is about 2.2, this will stop boiling. It no longer has any viscosity. So as the molecules move up through it, they don't disturb it. And it just goes what we call quiescent. You want to shut the lights off? Not quite focused, really.
Yeah.
Now, this quiescence will occur when this is around 32. So you can see we have about 100 millimeters of mercury to go. But it will only happen once. If we go back up, it doesn't go normal again. If you ever do helium experiments in your research, you can only take reliable temperature measurements above the superfluid point or below. But once you go below, you cannot go back above without shocking the system. Otherwise, your readings don't mean anything. I should explain a minute. In helium, there's a very tight correlation between pressure and temperature. If you know the pressure of the helium, you know the temperature. That's true as long as you haven't gone through the superfluid point and back up. So if it's normal, you're fine. If it's superfluid, it's fine. But once it's been superfluid, if you go back above the pressure of superfluid, you have to somehow shock the system, transfer against the bar, and it's something. So 72. So do we have any questions why this is going on? Does everybody understand what we're looking at here? Okay, you don't. So these dewars are silver, but there's a strip on the dewars where the silver is removed, and it's just clear glass, and the strip's on both sides. So the front strip is right here. Can you see that? And the back strip is behind it. And we're shining we're shining a light through the back slit, and we're pointing a camera through the back slit. And this is the camera looking through the back of this. We have enough helium? We okay?
Yeah, we do.
Okay. Okay, how are we doing for pressure? So we're at 50. Jerry, you need to crank it up.
Yeah. And I'm gonna get the baffle out of the way.
Yeah, okay, that'd be good. Well, don't worry about it. Other way. There you go. Up. Yeah, okay, that's a good image. Okay. So you see how that's boiling. We're 44. I don't know how accurate this gauge is. We're getting close. It'd be wise to watch this. Did I shut that off? I did not. 41. We got the valve. This is wide open.
Yeah.
Quite tore down there. I hope we can do everything. Oh, it just did it. I was wrong. It's 40. Did you see that? You see how it's not boiling anymore? It's just sitting there. Did you see that, April? Okay, everybody? So that's it. So now we have superfluid helium. We had normal helium, and now it's superfluid. Now once it's superfluid, we can do some fun tricks. One of the tricks is this little glass vial. Very nice picture, Jerry. Excellent picture. You see that glass vial? That's down in the superfluid helium. I'm going to pick it above the superfluid helium, so of course it's full of superfluid helium. And if I park it right there, can you move the camera up just a smidge so you can see the top? Park it right there. You'll see that it never stops dripping. Stop, right there, go. In fact, you can see that the level here is going down as this continues to drip.
Absolutely. There is no hole at the bottom. It creeps and it goes up and then down on the outside.
So there's no viscosity, but there's still, what's the property of it? It sticks together. I can't think of the word right now. That doesn't sound like the word I want, but anyway. So it's still
Surface tension.
Surface tension, yeah. It still has surface tension, but it doesn't have viscosity. And so it's just sucking itself out of here down there, just as if you had ever, in the old days, anybody ever have a water bed or anything where you use a tube to siphon, a hose to siphon the water out? It's sort of the same kind of thing, but there's no hose.
And when you look at these almost all atoms here are in the same quantum state. So what we see, I don't know how many billions of billions of billions of atoms, which all have the same wave function. That's what you see on this screen. Quantum mechanics before your eyes. It's just magnified, so that you can see it. And then it drops down.
Now what I love is, look how well you can see this. You can see this is the level of the helium. There's the drop coming off the bottom. It will just keep doing this until it fills up. Conversely, if we wanted to, we could let this thing get empty, and we could stick it down in the helium like that, and it would go the other way. So we should be able to fill it up to that line if we just wait a minute.
It went up just with the line.
Well, I don't think it's quite there. I think it's right here, isn't it? The gas bubbles from the nitrogen are getting in the way. Oops. I don't know. That was too bad I went the wrong way. Anyway, everybody see this and understand it. You have questions? The next trick's the good trick. Everybody good with this one? Nobody but got Kenny. And there we go. All right, here we go. So here we have the fountain, which is already working a little bit. So let me run the camera down a minute. I want you to see this before we actually make it work. It should be pulled up. Come on, there it is. There it is. Okay, so what we have here, this is about 1/2 millimeter hole coming out of this glass tube. And down here, this is just a glass device. I'm going to get all the way to the bottom of it. And this is the important part. So can you see these little black spheres? These are ball bearings. I took in the machine shop and I put them in oil and I hit them with a torch and got them all black and tarry and nasty. So they absorb light like crazy, which is what I want them to do. But the important part is down here. This part is what's called a sinter. Now a sinter is a filter. It's a ceramic filter, and they use them in chemistry. And this whole thing is made out of a sinter. So the sinter is like a porous ceramic material that you can pass fluids or things of small diameters through. So I got the smallest sinter they had, and then I got some very fine powder, polishing dust. And I took a pencil eraser and so I tried to plug the sinter. And when you get the sinter plugged enough, the only fluid that can pass through it is superfluid helium because it has no viscosity. So here's what happens. Through osmotic processes, superfluid helium goes through the sinter. The chamber, we're going to shine a bright light on these blackened balls. They will absorb heat. So once the helium passes through, it becomes normal. So it can't go back out. So this is a one-way valve. Osmotic processes cause the helium to go into the chamber, but once it's in there, it changes to normal, can't get out. So what happens is that little hole is the only escape. So as osmotic pressure continues to push more and more helium up here, we shoot out the top, and it shoots pretty far. We hadn't even turned the light on, it was already working. Does everybody understand what's going on? Jerry said, okay. Put it back down.
Hope you know what osmosis is. Raise your hands, those who are familiar with the phenomenon. So if you have, imagine you have some barrier, some filter which
All right,
allows...
get it here. See, it's already coming out a little bit here. Jerry's going to turn on the light. I'm going to lower it just a little bit. You see here? You're not getting it yet.
Okay, so it's not working. We have time to discuss what osmosis is. Let's forget about helium, think of a simple situation. You have some filter, you have some liquid, and you have some ions, which can
You don't have it yet.
through this barrier. Now what happens? Liquid goes and reaches its own equilibrium, but ions will stay on one side. And then they create additional pressure. They want to go, they constantly hit this barrier, but they cannot go back, right? They cannot go through, they go back. So there is an additional pressure. The same happens here. Superfluid helium can go through and tries to reach some sort of equilibrium above and below this filter. But normal helium exists only above it. So it creates some additional pressure. And that's how the problem works. Does it make sense? Is it clear to everyone? You see it.
Jerry? Can I say something, please?
Yeah.
I think you have to pull this back up this way. I think you're shooting too steep of an angle. I can't go like this.
Okay, again, who understands how osmosis works? Raise your hands now. Okay, those on the front row didn't hear anything. Well, I cannot tell.
Okay, so I'm just working.
Okay, is there another question? Do you remember that when, in the very beginning, so there was a demonstration that you get some helium in your mouth and suddenly your voice changes. Any explanation?
It's because the density is lower.
So
it's
So basically, like when the vibrations in your throat, because the density is lower, the pitch gets higher.
Well, you change the speed of sound, right?
Right.
But you have the same wavelengths because it's determined by the geometry of your own throat, right?
Correct.
So you have a different frequency. Does it make sense? You have different density, hence different speed of sound. You don't keep the very different speed of sound. Nevertheless, the wavelengths of the voice is the same, so its frequency changes. Does it make sense? But that has nothing to do with it. That's nothing to do with calculation.
Right here?
He was the first one to calculate the speed of sound.
Look through from the other side of the
Mistake of
finger.
100 years
Right
later.
there? Okay.
Environment that was negative 100 degrees Celsius.
How's that, like hitting him?
Like that, the voice would be down.
No, you cannot live into the environment. Helium has the temperature.
So what's, oh, we need to move that way?
Different density.
Okay, move that way.
No, if the density changes, yes.
No, the other way.
Then your sound producing system is not going to work. So you're doing a lot worse.
Well, just keep going, keep going. Okay, now I have to do this, just wait a minute, okay? Keep going. No, the other way, other way, other way, other way. Keep going, keep going, keep going, keep going, keep going, keep going.
So it is the temperature
That is?
with 150 times worse than There is actually one interesting thing about helium. We discussed that there are two types of helium. Helium-4, which you see here, and helium-3, which is Fermion, right? It's made of 5 particles, as we discussed. We discussed not 4, not 6, sorry. Just 1 neutron.
It's
Two protons, 2 electrons.
Oh, there it is, I see it. Yeah, okay, Jerry, Jerry, go that way, like crazy. Go, 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 go. Other way, other way, other way. Go, 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 go. Stop. Anything yet?
Okay,
Okay,
so,
keep going, keep going,
as
keep
we
going.
discussed, helium-3 is made of fermions. So again, it's even the same quantum already. You don't have all this nice phenomenon like superfluidity, but that's not true. At the temperature, which is about 1,000 times lower, helium-3 is actually also superfluid.
Do this once, I know.
Any explanation how this could happen? It's made of fermions. What's going on? No? No, what ionization is at low temperature?
Instead of everything going to the ground state, everything stacks on top of each other on the stage.
Well, at some level you can tell it this way, but actually there is a better explanation. Because everything stops on each other in simple momentum, it's not superconducting or superfluid. And that's a huge hint. Superconductivity and superfluidity is actually the same phenomenon. Superfluidity is maybe the most spectacular.
Why can't we get that?
So what's going on? So
Yeah,
when you take
is
two
it all the way
fermions,
up?
what can you build of them?
Yeah, that's, well, no, you're hardly up at all.
Yeah, Boson, right? Does it make sense? So basically what happens is very low temperature, helium-3 atoms overband
upside down.
of two fermions, which are already bosons. And these bosons are superfluid. Does it make sense?
Take the light. It's not enough for this far.
So I know a lot of new information today. Everything is very hand-waving, but at some point you have to stop writing equations and try to understand what's going on in nature. And you cannot always understand it just with some simple equation.
Yeah, that would be hard to do right now. We have a technical problem. We can't quite get our light to hit the balls. Yeah, let's try it. Let's just see if we can do it. Here, this is your job. Got it? Room lights, please. Thank you.
Any questions? So everybody was so quiet.
Which one's
Now you can ask the questions, right?
broken knife, please?
Is everything clear to everyone? Raise your hands, those who understand everything. Okay, the rest doesn't understand everything, so you must have questions. Again, raise your hands, those who understand nothing. No such people. Okay, you must have questions, you know the rules. No, that's an impossible situation. Again, raise your hands, those who understand everything but nothing. Okay, not so many people. So the rest must have questions. That's not helium on the screen, so. Go ahead. Jerry, watch.
Okay, we got the camera back. So let's get an image. What do you do with this one? Which way do I turn it here? You're looking at the side of the sewer. Very nice. Here. This thing's got this is missing screws. Push. You're pushing. You're not pushing hard enough, girls. Push harder. You're too engaged with anything. Of course, you do the turning. You ready? There. Okay, you got it. There you go. I'll do it from the front there. You need to go down. We're looking at the straight. There, oh, there it is, over there. Okay. Move the camera over so Sarah's not in it. No, I mean,
This is very difficult because when this was first demonstrated, that eventually resulted in a lot of variety physics. But interestingly, there was a huge gap. When this phenomenon discovered? Hold it down, man. When was superfluidity discovered? It was discovered in the sources.
you need to be where you
Well, the price was that so many
Strength plates.
so balance along the gap. No,
Yeah.
no, that's.
Oh, what the hell's going on?
Maybe demonstrate that with a leak somewhere.
Got one there, but it's a different story.
There it is. There it is. Oh, you gotta get your.
Try to do something better.
It's shooting like crazy.
All the way up.
Turn the intensity of the light down.
Okay, so what we see is something that remains liquid
You need
up
to
to
move
zero
that
temperature.
way.
But the room temperature is always against, right?
Okay, move out that way.
Now, can you tell me what elements are liquids at room temperature?
I actually know this. It's mercury and boron.
No, boron is.
I just chose the B.
Boron is, well,
No, not boron.
boron is a nice crystalline
What's the other word that? What's the other word? that- Barium?
Barium is an alkaline earth metal.
It's not there. You know, I know it starts with a B. What's the other outline that starts with a B?
Yeah, it starts with B. What is that? What is it? No, Well, okay, color, yeah, that's
I
key.
told you to bring
One
the
color,
left,
the
you got
other,
it?
there's normal conditions. Again, it depends how you define normal conditions. If you redefine the slightly, there are more than 2 liquids.
Gonna leave me now?
I'll be right back.
Bob, are you here?
Yes.
Okay, so that's bromine, right? A red liquid. You know that. You said
You said barium.
Okay. But barium is an absolutely different story. Barium is an alkaline metal
What are you saying?
and the most active on them. The only one
Okay, so
that
you
you
can do
can
that, right? This guy moves the camera back and forth and up and down.
If you slightly heat so, if you go slightly beyond our usual 20 degrees centigrade, you actually get two more liquid elements.
Oh,
What
no,
is
there,
it?
wait, stop, you're fine, you're fine, you're fine, my bad, there it is, okay.
One of
Okay,
them
so,
is extremely
tell me if I get it to go.
Replaced by Gregoro, that's easier. One of alkali metals. I think it becomes a liquid at around 40 degrees centigrade. I don't remember exactly. So there is another one which becomes more important. Which one? So again, it's not exactly. Completely improved conditions are element of storage, cesium. But in contrast to cesium, which you don't want to touch it extremely.
Turn the light back,
element
turn
you
the
can
light
put on your
on.
hand and see how it
Put that on
melts.
100.
What is the element which would melt when you put it on your hand?
Put this
No,
on.
lead.
There we go. Got it? Okay, guys,
There's a phone.
get their attention, Bob.
I did, they're looking at it.
Okay.
So again, now why is very important? People now use the thermometers instead of the mercury.
Okay, can you see that?
For semiconductor industry, even though-
Put your finger. Set the room lights off.
Okay.
You know, you see it goes up and down because I can't hold the light very steady. When I get the light just right, it shoots up. That's it. That's the fountain effect, and I apologize. We can do much better, but for what it didn't want to work for you today. Yeah, we're all set. Turn the lights off. Yeah. Turn the room lights on, please. Thank you. Okay. Any questions?
Is everyone other hand? You have no questions because you have to digest all this enormous amount of stuff? Or you just hesitate to ask? Sorry? Why it goes up? Oh, it goes up because of the subextension force, right? Everything, it wants actually to go up because of subextension, but it cannot because of viscosity, friction, right? There is, so yeah, everything is when you put it in a narrow pipe, it actually wants to go up. You can only see this profile of a liquid. There's somewhat bends. What is in the center is below. What is near the surface of the pipe is somewhat higher because subextension drags it down, right? But there is some friction. And viscosity, it doesn't let liquid to go continuously. It has to
Mercury has a positive.
Here's the difference.
That's right.
There is no viscosity.
So why you
If
asking
you
about
drag it,
mercury?
it just goes and goes and goes. Huh?
Every
That's called superfluidity.
fluid. Like,
Well, it's a critical story, but there is no viscosity. It's too advanced for this class, but the basic reason is that a lot of helium atoms have exactly the same weight
I have,
function. That's very
not
interesting. That's a both statistic thing.
they
They see them the same
Actually, I
thing.
just realized
It's very hard to create an isolation of the system. That's what happens. What is viscosity basically? You go and you try to hit the system, and on purpose you create excitation.
oh,
You have no
well,
excitation.
you're an undergraduate.
Just do nothing. You have to go, right? Does that make
demos are
sense?
not very popular.
No, it's such.
We do a fair amount in our graduate school.
Everything just get made on this ground statement doesn't care about anything. So it goes and goes.
A lot of places, it's like the first, the brain dead courses you get demos.
Yeah.
No viscosity because all these are also sitting in the ground state.
No, I haven't found it. No,
It's
it's
the
not
same
of us.
state. That's what
Yeah.
happens.
No, I love
Now, we can chat and discuss how this happens in more detail. There's a tricky thing. That's for what Landau got the Nobel Prize for the explanation of this thing. So not for the stuff we discussed in the previous two classes. But that's another story.
Why don't we continue on that gravity?
Gravity? Oh, gravity, no, gravity is too weak for this. Superextension is stronger than gravity. No. Gravity for such stuff. Again, think of the density of this thing, among other things. It's just 70 grams per liter. It's 14 times lighter than water. So what gravity?
So the helium will go down as where?
It goes down,
It goes up as
it-
well as goes down.
It goes down, but on outside. So, okay, let me make a picture of something like that. So there's the surface helium. Now, because of surface tension, we want to have those methods, okay? But then it just goes. Normally, this what every liquid wants to do. It wants to form some very narrow layer here. It likes extending the surface. It gives us more energy. But less energy. But unfortunately, it cannot really flow. There is too much friction, right? When the layer is very slow, and you have to be impressed exactly on this surface. And if something flows here, you develop enormous velocity gradient, right? You get enormous viscosity force. Unless your viscosity is exactly zero, then you just go. You basically have just a single molecular layer, okay? But then, when you reach the edge of this thing, you just go in the opposite direction because you still want to sink on surface, right? So you go, you accumulate here, and then surface tension is indeed not very high. So as long as you have a lot of surface and such low density and very little volume, surface tension completely dominates. But then you accumulate a lot of liquid here, and you just have so much surface, right? Most of it is inside. But then sooner or later, and it takes some time, even for water, you don't have very small drops, they have some decent size. Here, the same happens. After you accumulate really much, finally gravity leaves, and then you drop goes down. Does it make sense?
I have a meeting in my office. Just lock the door.
Yeah.
Any other questions? Okay, if everybody understands everything that he really must thank Dean for